I think it's better to keep it long, because otherwise a speaker gets hit by the word. I also would like to welcome the online audience. So we have Chaoran here, who was so kind to help us stream this lecture to the net. There was quite a bit of interest to join online. I don't know how many there are now, but there are a couple of people also online now for this lecture. So without further ado, are you ready, Chaoran?
Sorry, almost. We're just setting up some technical issues.
Yeah. So the idea of the procedure is that this is supposed to be mimicking a master level lecture, regular lecture on a master graduate, undergraduate level. And so Chaoran has about 3/4 of an hour for this lecture, and afterwards the committee will give some feedback and see what they think about it. Plan for the procedure.
I need to sit here somehow if I'm going to disconnect.
No, really?
No, I can play it one more time, but anytime I
maybe you can use my computer. I think that's.
Is it safer? If you could join the Zoom and share from your
I can try to go.
Thanks.
We really need a better solution than this.
Yes. I just thought it's an algorithm thing, right?
Don't we have some human in the loop? So we are talking about artificial intelligence on the one hand, that we can't get the slides up the projector.
Well, because it's too many humans involved.
All these humans in the loop solutions. Terrible.
Yeah, I guess.
Yeah. You managed to do this.
So you can start here. How are you like?
So second try. Are we ready now?
Yeah, I think mostly.
Okay, so it's okay now.
Okay. Okay. Thanks, everyone, and good afternoon. And, today I'm talking about. So welcome to my chat lecture. Today I'm going to talk about the explainable AI. So AI refers to artificial intelligence. So which is the simulation of human intelligence by machines. And this human intelligence includes reasoning, learning, planning, and creativities. So in our daily life, we have a lot of successful applications based on AI. For example, the self-driving car. And as I know, there are many cars they can drive in a certain road or autonomously. And also another important famous application is AlphaGo. And AlphaGo is the famous Go player in the world. This is a great achievement because the computation complexity of Go is very it's much higher than the normal chess and the normal boarding games. And also the traditional machine learning can't solve the problem, but AI solves this problem. And also, we also see a lot of successful example in healthcare. For example, with the help of AI, and the doctor are more efficient to extract the important information from the medical information. And also, I know some tools and the device that are based on AI can even help the doctor for some surgery. The last example is smart home. And as we know, there are more and more smart devices in our home, and they try to learn our preference and behavior, and try to make our life more easier and convenient. So then goes to the question, why we need the explainable AI? So the simple answer is sometimes the correct answers doesn't mean the intelligence. So here I want to share a interesting story to you. And this is a horse 100 years ago in Germany, and which is called Clever Hans. And this horse was very clever because he can do some simple mathematical calculation by using his feet knocking on the ground. Yeah, but afterwards people found, and if there are no people around the horse can't figure out the calculation. So the reason behind is the horse tried to watch people's facial reaction to do the mathematical calculation instead of understanding the meaning behind. So this is an interesting story. And also we have a lot of examples to show how wider explainable AI is important in our daily life. For example, the first one is the financial models used in the bank. And most likely, this is required by the law for the bank to ask the financial model to be explainable. And the decision is very important. For example, how much money we can borrow from the bank. They need to have a very explainable model to do this. The second example is the medical diagnosis. And this is very critical to our humans' life. So the decision is very important. So we need an explainable model to do this instead of being a risk of people's life. Another example is some models used on the court, and we must to make sure this kind of model they can behave in a proper way, and also they need to behave in a non-discriminatory manner. And the last example is a self-driving car I mentioned before, and sometimes it will have some accident if it's abnormally. So we need to explain and what happened and why this happened. Then afterwards, then we can try to avoid the accident. So this is some example in our daily life why the explainable AI is important. So when we're talking about interpretability and explanation, and we know some models are intrinsically interpretable. For example, the linear model is very easy to understand. We can just to look at the weights, and then we know the feature importance very directly. And another interpreted model is a decision tree, and this is also very straightforward to understand, and we can follow the branch of the tree and to understand how the decision made and what's the condition behind. And also decision tree can be powerful to solve many complicated problems. But then in that situation, the decision tree will be super complicated, then it's very difficult to interpretable. And compared with the interpretable models, deep learning are very powerful. As I mentioned before, there are a lot of successful applications based on the deep neural networks, but most likely they are black box. So in this lecture, I will try to introduce some methods to make the deep learning or deep network more interpretable. Then we come to see a simple example for the image classification for the dog. And the classifier told us this is a dog, but we want to know why this is dog, right? So in general, the explanation in AI can be categorized as local explanation and a global explanation. For the local explanation, we want to answer the question, why do you think this image is a dog? And for the global explanation, we want to know what does the dog look like in the AI's eyes. So we want to understand these two questions. So in the next, I will introduce the local explanation first. So for the local explanation, so we want to explain the decision, which component is critical for the AI to make the decision. For example, the dog picture. In my eyes, I would say the dog ear and the mouth, and also the leg, make me think this is dog. But this is my opinion. And so in general, and if we have object X, and this can be image and text. And in our example, it's a dog image. Oh, sorry. And also we have the components for the object. If the components are x1 to xn, and the components for the image, it can be pixels or segments, and for the text, then it can be a word. So if we do some modification or removing some of the components, if it can lead to very large change of the decision, then we can know, okay, this part of the components is very important for the decision. So then based on this idea, then we know how to find the important components. So based on the method I introduced before, I want to show 3 examples based on the algorithm. So these 3 pictures, they both have the true label. So which means if I put the first picture into the network, it will tell me this is a Pomeranian dog. The second picture will be car wheel, and the third picture will be Afghan hound by the neural network. So the algorithm is we can put a small gray box. Here is a small gray box. Okay. Yeah, and if we put the small gray box on the face on the Pomeranian dog, then most likely it's difficult for the neural network to know, okay, this is a Pomeranian, right? Then we have the visualization of this kind of algorithm below. So the blue part means the low confidence of the to classifying this dog as a Pomeranian. You see, here is very reasonable because when the gray box to the middle of the picture, it covers the face of the Pomeranian. So, but the red part means the high confidence. So, of the dog being classified as a Pomeranian. If we look at other results, you can also see the network distinguish this part is the car wheel. So mostly very reasonable in my eyes. And also the third picture is a little bit difficult because we have the man and a woman, but and also the dog, but the neural network still can find the shape of the dog. So based on this visualization results, then we can say the network learned something meaningful. So this is a good example of how we look at the neural network by looking at these pictures. And the next, and also when you use this technique, you need to be careful for choosing the size of the gray box. For example, and you can imagine, and if the box is super small, it's like 1 pixel, then everywhere will be not important. If it's super big, then everywhere will be important. And also the color of the box is also important. Depends on your pictures you use. Here I use gray box, but if you use other type of image, you need to keep this in your mind. And in the next, I want to introduce other way to the local explanation, which is called gradient-based salience map. So we have, so for example, I still talking about the example in image classification. For example, we have the image which can be represented in pixels x1 to xn, and we have yk. Yk is the probability of the predicted class of the model. For example, we have a dog picture. So the yk means how much probability of this picture being classified as a dog. So this is the yk means. And afterwards, we can add a small noise, delta x, to 1 pixel of the picture, and to try to see how much influence of the YK. If delta X leads to very high delta Y, which means this pixel is very important, right? So then we can compute this importance by using delta Y divide delta X. Actually, this is the gradient. So we can use the partial derivative to compute this gradient value. So here are 3 examples based on this technique. So we draw the visualization, which we call it salience map, on the bottom of each picture. You see the light color means high gradient. And based on these 3 pictures, we can say the network learns the contour of the animals when it makes the decision. So in my eyes, this network is relatively good. They can distinguish the animal, not look at the background or something. So I also want to show some example of a bad model recognized by the salience map. And before all the example, they are good models. And here is a bad model. And here is a picture, is a horse picture. And the neural network can successfully categorize this image as a horse picture. But afterwards, when we look at the salience map, you see the high salience, you see the high gradient part is on the left corner. That's not the horse, right? But afterwards, we think, what's in the left corner actually is a caption in the left corner. So the network found, okay, many horse pictures, they have the caption on the left corner. So let's make this. So he found this kind of rules, but this is not good, right? So based on this, we found the explainable AI is very important. Also, I want to show another example about it's also a bad model. So the model is also solve the image classification problem for the Pokemon and the digit. And on the left is the Pokemon, on the right is the digit. So we expect the neural network can classify in a correct way. So afterwards, we do some training and testing. The result all are super good, almost perfect. So which means the network can successfully categorize the Pokemon and the digit. But afterwards, when we look at the salience map, it's horrible. Yeah. If we look at the background, all the high salience, all the high gradients are on the background instead of the animals, right? So which means the network only look at the background, then he knows this is Pokemon or this is digital. This is totally what we want the network should behave. So what's the reason behind? Afterwards, we figure out because all the image of the Pokemon are PNG and all the image of Digimon are JPEG. And if you know PNG, on the corner is the PNG. The background of PNG is transparent. So if you load into the neural network, it's a black color. So the network just found the black color is Pokemon. Yeah. So this is not correct. So the machine discriminates Pokemon and the Digimon by the background color. So this is also showing importance of the explainable AIs. Yeah. So and as I mentioned, the local as I mentioned, the gradient-based local explanation, and actually they have some limitations for the technique. For example, the first one is noise gradient. For example, we have a picture of gazelle. It's something like sheep or something. And after we use the gradient-based salience map, then we get this picture. There are a lot of noise. But we try to improve this, so we use a new technique called smoothing gradients. So the idea is very simple. We just put maybe, for example, we put 100 noise on the original picture, then we can create 100 new picture. Then we compute 100 gradient-based salient map. Then we make an average of the 100 salient map. Then we get the smooth version of the salient map. You see the picture on the right is much better than the middle. And also another limitation is gradient saturation. So what's the gradient saturation? And I give an example here. For example, the neural network want to differentiate whether an animal is giraffe. So one important feature of the giraffe is the neck length, right? If the neck is very long, so mostly we all know this is a giraffe. But if the neck is long enough, so it won't make us think this is a super giraffe or something like that, right? So which means if we do the gradient calculation on this point, then it will be 0. So then at this time, then the gradient can't reflect the importance. So when we use the gradient-based technique, we need to be aware of this situation. So how to solve this problem is we have an alternative way, which is called integrated gradient. But during the time, I'm not going to take the I'm not going to talk the details about this. So next, I want to show the overview of all the gradient-based techniques for salient maps generation. You see, we have already introduced the typical gradient algorithm, and also we introduced the smooth gradient, and also we mentioned a little bit about the integrated gradient. So all the techniques, they have different kind of strengths and the weakness. And if you want to use them, you can go to more details about which one is more suitable for your task. So after the local explanation, I want to talk about the global explanation. So the global explanation means we want to explain the whole model. So what does this mean? This means we want to know what does the object look like in the AI's eyes. For example, here are a lot of nice pictures. We draw based on the tree model. And this is show how the AI thinks, how the red shank and how the ant and the monastery and the volcano look like. You see, most of these pictures are quite authentic. If we can draw something like this based on the AI model, then we can have some confidence about, okay, this AI can understand something similar to our human being. Yeah. So we want to achieve something like this. So how to do this? I will use an example, convolutional neural network. So on the right is a typical structure of the convolutional neural network. We have the convolution layers, and for each convolution layers, we have a lot of filter. The filter is used to detect the pattern of the picture. For example, we have an input, and for the input to the neural network, then we can have the filter output. And for each filter, we have a feature map. For example, here, the blue matrix is the output of the filter 1, and the red matrix is the output of the filter 2. So imagine if we have an image X, if we put into a neural network, then we can get some value of the filter in a matrix. For example, if we get a lot of very large value in the blue matrix, this has some meaning, which the meaning is that this image X contains the patterns filter 1 can detect. So then this comes to a question. Then we are curious about what kind of image X makes the filter 1 can detect, right? So we want to see how it looks like, at least. So how to do this is, so we want to create, so how to do this? Imagine now we don't have the input. Before we have the input X, and now the input is unknown or variable. So we want to generate the input picture. And also the value of the filter 1 can be represented as Aij. If we use this equation, we try to maximize the Aij. Then we can get we try to maximize the sum of Aij, then we can get the X star, and which is the picture we want to see. And for this equation, we can use the gradient ascent to solve this equation. And then the X star is what we want, and which contain the pattern filter 1 can detect. So next, I will give an example about how this algorithm works. And this example is based on the MINST dataset. And if you heard about MINST dataset, this is for the digit classifier, for the digit classification, for the handwriting. And I have a screenshot of the MINST dataset. And this is about 1, 2, 3, 4 to 9 digit handwriting. So the network try to recognize which digit is the picture. So I use this then up to the as an example to show how the image for the filter, what kind of image can make the filter can contain the pattern the filter can detect. So I choose the filter from the second convolution layer, which is 12 different pictures. And you can see, we can see something here, right? For example, we see the picture on the left corner is vertically. So which means the filter can, which means this filter is responsible for some vertical stroke or something. And also the picture on the right corner is diagonal. So it's also some features or patterns the filter can detect. Yeah. So when we figure out how the filter pattern looks like, then we come to another question, which is the final question. What does a digit look like for CNN? We still use the MINST data set as the example. So we want to know what type of the digit picture makes CNN think it's 1, 2, 3, 4 or something. So we can follow the similar algorithm. So we just need to maximize the output of the CNN, which is a class for the which is a class can be represented as yi. So we can maximize this, follow the similar rules I introduced before. But this is the result. All are noise, you see. So which means if you put the first picture or three, so all are noise picture. So which means if you put this picture into the neural network, it will tell you this is 0, 1, 2, 3, 4, 5 something. This is totally not good, right? So why this happened? So this means deep learning networks are very easy to be fooled. But if you heard that there is a terminology called adversary attack, then you won't be surprised for this. And here is a simple example of the adversary attack. For example, the panda picture shown on the left is categorized as panda by the neural network with 60 confidence. But afterwards, we can add some very special noise to the panda picture. And after we add in the noise, it still looks like panda in our eyes, right? But when you put it into the same neural network, it will tell us it's a gibbon, which is something, monkey or something, with 100% confidence. So network can be fooled by human with careful design. So that's why we can't get the good results of the picture I showed to you. So then, how we solve this problem? Because we expect to see some picture with 1, 2, 3 features in our humans' eyes, right? So we need to add something called. So we need to add a constraint to the optimization process. The constraint is called Rx. And what's the constraint? How to design the constraint is very empirical. For example, we know the digit is composed of some strokes, right? And the strokes are colored in white, and also the rest part of the picture is black. So we can make and also the white area is very small compared with a background. So we can make a simple constraint, which is the sum of the pixel value. Then we try to minimize the white area. Then this can be one constraint. And there are so many constraints you can design. This is just a simple example. Then afterwards, we get better results. You see this better result. For the first picture, I think 0 is quite clear, right? And for the 6 is also I can recognize. And 8, I also can understand a little bit. But others, I'm not sure. So the result is highly dependent on the constraint that you design. Yeah, it's very empirical. So if you want a good result, you need to be careful the design. Okay, then I show some better results. This is how the neural network thinks different animals and the table and the car looks like. Yeah, you see this result is quite good, right? At least most of them I can understand based on my eyes. But this result is not easy to achieve. You need a lot of parameter adjustment and the constraint design. But at least we can get something like this then to achieve the global explanation. So till now we have introduced the local explanation and also the global explanation. Actually, we can also use another model to explain another. For example, we use an interpretable model to mimic the behavior of an uninterpreted model. This can be also a nice way to explain. For example, we have a black box, which can be neural network. We have input and output. This is difficult to interpretable, right? Then we also have a simple model, which is a linear model. We have the same input of the black box, but we have different output. But we try to make these two output as close as possible. If they are as close as possible, then we can just look at the linear model to understand the black box, right? But the reality is, as linear model is not powerful enough, so this can't be as close as possible. But the idea is nice. We can use this idea to mimic the local region instead of the whole picture. Yeah. So next I will introduce how to mimic the local region. And this idea and the algorithm based on this idea is called local interpretable model agnostic explanation line. So imagine we have a curve, and this curve is a blue curve learned by the black box, which can be neural network, for example. Then we want to explain one point of the curve. For example, the red point we want to explain. And afterwards, we can do some sampling near the point. For example, we choose 4 points. They have the same distance in the x direction. Then we can have 5 points. Then we use the 5 points as a base to fit a linear model or other interpreted model. Then we get a linear model, right? Then we can use the linear model to interpret this local region. Then we can understand a little bit about the black box. But by using this method, you need to be careful for choose the sampling, because you can choose the sampling. The distance of the sampling is very important, and which will lead to different results. Yeah, when you use this. Yeah. And next, I will use an image classification example based on the LAM algorithm I introduced before to illustrate the results. And this network is for the floor classification. And in the beginning, we want to choose data points. We want to explain, right, the first step. And the data point here is the image. It is the floor image. And afterwards, we want to sample do some sampling of the image. As I mentioned, there are so many ways of the sampling. For example, you can add some noise to the picture, and also you can delete some pixels of the picture. But the most common way is to, based on the segmentation, you can look at the right side. We do some segmentation, and afterwards, we can randomly delete some segments of the picture already segmented. Then we get 3 pictures here, and then we put this into the black box. Then we can get the confidence about how much % confidence whether this is a fraud. For the first one is 85%, second one is 52%, and the last one is 1%. So after do this, then we go to the third step, which is we try to find a linear model to fit to get the same results of the black box. And if we directly put this into the linear model, then we will face 2 problems. The one problem is that the input is there are so many pixels in the input. Then it's very difficult for a linear model to do the fitting. So this is the first problem. The second problem is that if we finish the fitting of the linear model, there are so many weights for the linear model. Then it's very difficult to interpret. For example, they have 20,000 weights. Then I don't think humans are able to understand. So the common way is we do some feature extraction for the original input. We can do some dimension reduction to reduce the original dimension of the picture to low dimension. For example, this can be based on the segmentation we introduced before. We have n number of the segments. Then if the segments is deleted, then the xm equals 0, and if the segments exist, then it's 1. Then we can get a relatively small vector to represent the original input. Then we use this to fit to the linear model, then to get the linear model fitting. For example, then afterwards we get a linear model like y equals w I x I blah blah blah. Then we can look at the weights of the each components, each segments. For example, if the weights very close to 0, which means this segment is not related to fraud. If the weights are positive, means these segments can indicate the image is a fraud. And also, if the weights is negative, then it means the image is not fraud. So based on this, then we can do also do some local explanation by using a linear model. And next, I would like to show some examples, explanation examples based on the line algorithm. You see the picture on the left. This is a dog playing guitar. And if we put this picture into the Google Inception network, it will tell us 3 top classes. The first one is electric guitar, and the second one is acoustic guitar, and the third one is Labrador. And for each of the class, they also show us the segments are important for the network to make the decision. I think I can understand the first one because the handle of the guitar seems the electric guitar. Maybe, I'm not sure. But for the second, it's not very understandable for me. But at least it's not the close of the dog to say this is acoustic guitar, right? But for the last one, I think it's very good. The hand of the dog, the network think this is the reason he make for the Labrador classification. So based on this algorithm, we can so with the help of this algorithm, we can do some good explanation. So in the future, and I have introduced several methods. So in the future, we hope we can have a scenario like this. For example, we have a training data set of a lot of pictures. Then afterwards, we put this into a neural network or some smart learning process, then we can get an explainable model. And afterwards, then we put a cat picture into this explainable model. Then it can directly tell us, okay, this is a cat because it has a fur, it has a whisker, and it has claws, and also it has the ear feature like this. So we can have this kind of explainable interface. Then the user can interact with this explainable interface to have more insight of the design of the deep neural network. If the result is not good, then he or she can back to redesign the deep. Based on this structure, then we can understand why and why not to make the decision. And also we can know when the model will be successful or it will fail. And also we will know when to trust the model. And also we know why the model may make a mistake. So this is, I hope in the future we can achieve, then there will be perfect. So in the end, we go to the conclusion. So for the first conclusion is we can improve the artificial intelligence based on the explanation. As I mentioned many examples, and we can improve if we find the right way. And also second conclusion is the goal of the interpretation is not completely understand the deep learning. You don't need to know all the details of the deep learning because it's very time consuming. So you only need to some important things. This is because the definition of the interpretability is not defined because this is very subjective. This is very subjective. Something can make me happy, but maybe not make you happy. So I think the good explanation is make maybe most people comfortable or make your customer comfortable or something like this. And also the last one is, I think you don't need to be afraid of the deep learning, the black box, because our human brain are also black box. Yeah, we follow people's decision every time. We are not panic. So because I know many people in the industry, they are afraid of the black box. So just try and to see how it goes. It's not that panic if we have a reasonable way to make this more explainable. Yeah. Yeah, so that's all of my lecture. So thank you very much. If you have some questions.
Thanks, Chaoran. We definitely should also see whether there are questions. So to explain to how this nice picture, you add a constraint to like not have like just noisy image. But how do you choose this constraint? I get the feeling that if you choose any constraint, I can get any image of output because it can basically.
That's why I say how to choose a constraint is very empirical. For example, for our example, that's a digital image. So we know the stroke is a white color and the background is black. So we can choose a constraint like we try to minimize the white part. So this is one way to choose the constraint. But for other situations, for other images, you need to know some knowledge about the picture you are processing. Then you can design the constraint. Yeah, so this is very empirical, not easy. So that's why I say some results, they need a lot of parameter adjustment and so yeah, training, and then they can get the beautiful results. That's not easy for us to directly get. Yeah.
So, yeah, when you do these saliency studies, for example, do you see a systematic difference between whether you use a picture from the training set or a picture that is new?
If you use the picture from the training set, I think they won't have big difference. I think they are consistent. Yeah.
So the ones you showed here, they are new pictures.
Yes. They are both new pictures. But even you choose the picture from the training set, they also have the similar salience manager, the salience map, because the neural network, they follow the same rules. They made a mistake, so they also made a mistake in the training. But it's better to use something the network have not seen to test. But I would say if we use a training image, then will be similar results. For the Pokemon Digimon example, if we use the picture, if we use the picture in the training set, then we're also the city map. The gradient is also on the background. Yeah, similar. Yeah.
Actually, I have one. You showed us the line technique.
Yeah.
And you very well explained that if you build your linear model on the basis of all pixels in the segment, then you have the problem that you get so many weights that they are again difficult to interpret. And you showed that you would have to do some extraction or feature extraction or dimension reduction, as you said, in order to bring down this number.
Yeah.
But don't you just shift your problem to that stage? Then I imagine if I use a highly complicated dimension reduction technique like TSLE or UMAP or whatnot, then it could be again difficult to interpret these weights because the X1 and X2 are kind of difficult to understand what they mean.
Yeah, so that's why I say the common method is like based on the segmentation, because there are so many ways for the feature extraction. So we need to choose a way more easy to be understandable for the people.
But I also thought that you have to do an extraction per segment, because within each segment you have very many pixels, right?
Yes, but for each segment, we only label it to 0 or 1. If it exists, for example, if I go back to so it's very easy, it's not complicated.
So here I thought that you build your linear model based on the pixels in the chosen segments. Is that wrong?
That's wrong. 1% or not present of the segment.
And we have the picture, and afterwards, for example, the first picture maybe have 100 segments, and then we look at the segments.
I think I understood my misunderstanding.
Yeah, then we have maybe 100 dimension vector, then we put it to the linear model.
Yeah. Thank you. More questions? David?
Yeah, maybe given this is a business talk, maybe that's the wrong question to ask. But are people doing this kind of thing also for sort of time series?
Yeah, sure. Yeah. I think also people use this kind of knowledge for the time series in the recurrent neural network. But now most of my content today is about convolutional neural network for the image classification. But they have the similar things. Yeah, for the time series. Yeah, you can go to check. Yeah, but the basic idea is like this.
For more hands.
I have a question. You said that the interpretation itself is vaguely defined, because what does it mean that we explain what the machine does?
Yeah, it's very subjective.
Isn't there also like a really big problem with confirmation bias? I look at this thing and say, oh yeah, this is what the machine thinks, but the machine thinks something else, and those that we look at the same salience map.
Yeah, so you need to have some standards in your mind before. So that's why I say it's very subjective. Yeah, so this can be biased because different people, they have different kind of standard. So that's why I say maybe if this can make you feel comfortable and happy, then you just accept.
That's exactly what I say. Like if you target the customer or the consumer, you try to make him happy, then you're really falling into this trap of confirmation bias. You show him whatever he's happy with, and you still don't know anything about the machine.
But at least we have some common sense, right? We have some common sense of whether this is explainable or not. It won't be too extreme. Yeah. But but they have some paper about some standard, but not well defined.
Some kind of formalism, I think, would be.
So it depends on case by case.
That's maybe one of those cases where again it's easier to say when it's definitely going wrong, rather than saying that maybe it's right.
That's a good point.
Okay.
At the beginning in your motivation, you mentioned that it's actually something desirable to have explainable AI. You mentioned, for example, banks. But like, for example, credit institutions, they switched from explainable models to neural networks because they couldn't accept rules where somebody, because they have different ethnicity, gets a bad credit rating.
Yeah, sure.
So being able to be black box is at the same way, don't you think, also a feature? There has been,
Also a feature of the.
So it's basically, there has been a lot of research that what is considered black box is not actually very black.
Yeah, for example, you don't need
learn something about the training data.
Because the black box have different scales, and if you're super deep network, then it can be super black. Then you can just reduce to a shorter one, which you can acceptable or something.
What about overlearning? Overlearning?
You mean overfitting or something? Yeah, and this is what often happens for the deep neural network, and also some of the methods I introduced here, and also can be a way to distinguish overfitting. For example, for the convolution neural network, you can look at the weights to visualize the weights of the filter and also the feature map, and to see what it has. Sometimes, if it's all noise, then you need to be careful whether this is overfitting. Then you need to go back to do some adjustment of the hyperparameters. Yeah.
If I may comment on that, okay, I mean, the one thing that Chaoran said is that under GDPR, for example, you are obliged by law to explain the decision. So if a customer requests an explanation for the decision, then you are obliged to provide one. So that's the law. What that means is, of course, again, subject to interpretation. You can print out the ways of your explanation, right? I mean, so we are backwards by. I think that's the background.
Yeah.
Very good. Yeah. Okay.
Just one more. I mean, one of the features of deep neural networks that's also used during training is shift invariance. So you want to detect an object if it poses different, if it appears in a different part of the image. Doesn't this totally go against these very simplistic saliency map approaches, where even after, like the second layer, you already expect to have shift invariance, and therefore you would only expect to see noise in these maps? Because, like, why would the network prefer like the dog in the middle of the picture? It's basically a dog everywhere. That's exactly what it has learned, and then it looks like noise. So I think it's totally normal.
You mean, for example, there are many dogs in the picture?
No, it's like dogs in different positions, different places. But some in the left, some in the right.
The saliency map is specific to the one picture you're feeding in. It's not an image of the network itself.
Yeah.
So if you feed in a picture that's transposed, the salience map will also transpose.
Yeah, I was so saliency map is the wrong word. The ones where you generated the pictures that the network filter would like to
So
see.
the global explanation.
Oh, you mean the global explanation?
Yeah, part of the talk.
Yeah, but we saw that, right? The example that worked was actually we saw the flamingos everywhere, basically, exactly because of it. Yeah. We could take one more question, but then we probably have to respect everyone's time also. Okay.
Do you think current explainable AI techniques are more targeted at AI developers or at consumers who are suffering the consequences of AI? Forgive my negative phrasing of that. So, for example, if you have a medical AI context, and is it more for the developers, these things, or is it more for patients to understand why decisions are made?
I think now it's more for the expert. Yeah, I think But I think in the future, I think we expect maybe the normal customer, they also can understand how the decision made, yeah, in a more easy way. But now maybe, for example, now the expert, they need to look at the weights and also look at the, for example, the salience map or something like that. Maybe less more straightforward for the normal people. So you need some basic training of, yeah.
Okay. I would suggest that we now thank Chaoran once again. I'm also happy that many of you came to attend the lecture. I think the general audience can now do whatever they need to do.